Oops, hi everybody. So today this is the title that says that I will talk about the quasi-thermal noise and shot noise in space plasmas. Why is this going? Okay. So this is actually one part of the PhD thesis. It was done in commandership between the Paris Observatory and University of Belgrade Department of Astronomical Mathematics, with great help and collaboration with all these wonderful people. So what was actually, before I say what was actually the task, I will just say a few words about the method that was used or developed during the thesis. So what is the quasi-thermal noise spectroscopy? Well, we have the electric field inside the solar wind. So we have the solar wind, which is actually chaotic movements of protons and electrons, and we have the simple radio antenna inside. So this fluctuating electric field is measured, and once we do the frequency spectrum, it looks, well, a bit like this. So this noise is actually coming just from the thermal motion of these particles. And we don't say it is thermal, we say it's quasi-thermal because the velocity distribution function of particles is not Maxwellian, so it's actually not thermal environment. And here we have several regions. First one, this is the peak. Okay, we like to see the peaks in general because they usually provide some info. And the info here is that it is just at the plasma frequency. So from here we can directly determine, without knowing anything about the environment, we can determine the density, total density of the plasma, of the electrons, to be precise. So the part over here at high frequencies brings information about electrons. Here we have info from the shape of the peak about suprathermal electrons. And here we have the information about protons. So depending on parameters from each of these populations, these parts of the spectra are going to look different. And there is some here a bit of a gray part. And this gray part is actually the shot noise. The shot noise is the noise that is not coming from the environment, from the electric field of the environment, but just from the physical impacts of a charged particle onto the surface of the antenna. So it just hits the antenna and then provides some signal. And this signal depends actually on the geometry, and more precisely on the relation between the antenna length and the antenna radius. So, how much is it important? I will show you two missions. We can recognize this shot noise slope, this black slope from the previous picture, as the frequency to the -2 logarithmic slope. So we have two previous missions, which have done very successful in the solar wind. This is IC3 and this is wind mission. And these are some examples of the spectrum. So this is 50 meters, 45 meters antenna. Both of them have the antenna radius which is less than 1 millimeter. So it's very long, very tiny, and very good for the thermal noise, because there is no shot noise at all. Here is the proton part, here is the electron part, here is the plasma peak, everything is readable, and the shot noise doesn't even exist. When you do the theory, it appears somewhere over here. So at these previous missions, we didn't care about the shot noise, but on this stereo mission, this is a NASA mission, which I will explain a bit later what this mission does and what is the objective. But what happened on this mission, we have 6-meter antennas. These are these three antennas, which we can see on the figure. And these antennas have over 1 centimeter in radius. So it's a very simple stick. And this stick, on this ratio, the length over the radius is around 700. So basically everything we observe is the shot noise. We just observe impacts and more or less nothing else. There are some other small contributions, but it is mostly shot noise. And it overwhelms all other contributions. So instead of using just very simple by fingers theory, which was used in previous missions, we said, okay, shot noise just makes number of particles times some basic signal. I will explain a bit later. And nobody cared about the precise theory of the shot noise before this mission. And at this mission, well, we have short noise like this, so we need to calculate some physical parameters that will give us information about the shot noise. And the first one is and this stereo, both stereo spacecraft had very good, very reliable, very precise particle analyzers. And these particle analyzers were made to provide info about the electron density, electron temperature, proton density, proton temperature. So everything was supposed to work perfectly without using any of the thermal noise methods. But the problem appeared in 2006 when two spacecraft were launched, and it happened that these two perfectly made electron analyzers are actually completely malfunctioning. So we can give a small digression why this happened. Simply the mass spectrometer that is used has an entrance, so the charged particle enters the spectrometer. Then in the electric field it falls down to the detector. From the location of the impact, you can measure the energy of the electron, very simple stuff. But the problem is this entrance must not charge. If it charges, then you have problems. And of course you test it on ground before the launch. Then they launched the spacecraft and they found out that actually at a temperature which is lower than minus 100 Celsius, these entrances actually get charged to around 45 volts. So all the electron data below 45 volts is just we cannot measure it, does not exist. And this is why at both stereo, so we have stereo ahead and stereo behind. If here is the Earth, it's not visible. So both of them are using the orbit of the Earth, going around the Sun. But stereo ahead is going ahead, a bit faster than the Earth. And the stereo behind is going a bit slower. So observed from the Earth to the Sun, they're going like this. And now what we want to do is to use quasi-thermal noise in order to obtain some of the lost data. As it was this morning explained, the stereo is based on simultaneously observing the Sun and the coronal mass ejections, and in parallel doing the in situ electron measurements. But the problem is that we suddenly found ourselves without any in situ data, at least not for electrons, and we want to use quasi-thermal noise to obtain this data. So from here we just need to, first we need to accommodate it for this mission, and then we need to validate the results somehow. Normally we would validate it with these electron analyzers, but since they don't work, they use wind data, data from wind mission, which is very good. I will explain it a bit later on. And then, once we establish the method, then we perform a complete study on the entire database. So now we have around 11 years of measurements. Resolution is around 40 seconds. Okay, so, and of course everything will be made available to the community once it is done. So, yeah, and afterwards, the same thing will be applied for the solar orbiter, because the thermal noise of the solar orbiter will be very similar, because the antennas will be very similar. So, okay, how the shot noise works. The basics are very simple. We have the Sun smiling over here, and we have the antenna. So the antenna is illuminated, and we have, if we zoom this part over here, we have some photoelectrons from the illuminated part. On the other hand, we have the electrons that are impacting randomly from the plasma. In the solar wind, we have around 10 times more of these electrons than of these ones. So, in general, the surface gets positive, and when it gets positive, it brings back some of these electrons that were previously pulled out. So how do we treat it? First, what we had before was a simple treatment. So this is the antenna potential with time. We have the electron that impacts it, the potential, either if it impacts or it leaves the antenna. The potential changes for some value, positive, negative. And this value is, of course, basic charge over the antenna capacitance. This depends on frequency. And the noise is actually the signal from one electron times the flux, times the number of electrons. And the electron flux determines the signal. This was actually done with very approximate expressions before, so we had to develop the more precise values of this flux. And of course, number 2 comes because we have photoelectrons, we have plasma electrons, so the process is completely mirrored up, and there's these 2 factors. So, okay, this is a process that lasts around 0.3 microseconds. So here, when we analyze it in this way, it is important to note that we neglect some things. First of all, we neglect the plasma collective effects, which we can do below the plasma frequency. So, as I said, our signal is just one electron signal times number of electrons, no collective effects. And we neglect the returning photoelectrons, which we can do below 300 kilohertz. And we approximate this fall of the potential, which was like this. We approximate it with the step function, which we can basically do again below 300 kilohertz, and the strongest condition is below the plasma frequency. So we can use this method below the plasma frequency at this point. Okay, so I will make a bit of a digression, because as it is well known, it is the kappa distributions that are actually observed in the solar wind. So this is the Maxwellian distribution by velocities, and this is actually the non-thermal or the kappa distribution, which is a generalized Lorentzian, and which is characterized by temperature, given by the thermal speed, but also with this kappa parameter. So the kappa parameter is actually the measure of the fast electrons. If the kappa parameter is low, then we have a lot of fast electrons, and as it increases, we have less and less of these superthermal or fast electrons. With kappa equals infinity, then we have just a simple Maxwellian. This is basic stuff, and why we use that? Because this kappa distribution fits better to the observed electron velocity distribution functions. In general, it fits better on all missions. It's shown here. I don't know if you see this. This is a combination of 2 Maxwellians, which actually doesn't fit so well. So we use the kappa distributions, and then what we need to do is to determine the flux of the electrons that impact the antenna for the kappa distributions. Of course, we have the signal, the single value here, so we don't use 2 Maxwellians, no combination, just a single electron temperature value. Okay, so we calculate the flux using the orbital limited theory. This is some surface of the antenna with some potential electric. We have the particle coming from infinity with some kinetic energy. Then on the road it gets some potential energy from this charged surface. We assume no collisions, which is always true in solar wind. And the condition to reach surface is very simple, but what is actually a bit more complicated is to calculate this flux for this kind of velocity distribution. So we developed this basic expression, and there is a proof 4 decades ago given that we can actually use this for any kind of isotropic velocity distribution. So from here, we can link the shot noise level to the moments of the velocity distribution. And this is what are we going to do. We are going to link it the first moment, which is density times square root of temperature, to the level of the shot noise. And we did this for the planar geometry, cylindrical, spherical. Of course, in theory, the surface potential can attract or repel electrons. We neglect protons because the thermal velocity of protons is way smaller than the thermal velocity of electrons. Okay, so from here, on the cylindrical antennas, this is the well-known result for the Maxwellian. This is the complementary error function. And for the generalized Lorentzian, which is the kappa distribution, we have a quite nasty result, which includes some hypergeometric functions and some other factors. So I'm not going to analyze this mathematically, because it's an endless story. I will just plot it to the figure. And we have the correction of the flux, how the flux of the electrons that impact the antenna actually increases with increase of the potential. So this is this factor, which is charge times potential times over the temperature. And this is the correction factor depending on the kappa parameter. So actually it increases quite a lot if we have a lot of superterminals. The same was done for the sphere, but I will show it here due to time limit. From here we accommodate it to the stereo emission. So we have this frequency range of measurements. We have the noise from protons, we have the noise from electrons, we have the noise that comes from the instrument, and we of course have the shot noise. So the shot noise is of course dominating, and since it is dominating and depends on the flux, it's very important to use these results given by the orbit limited theory. Also, there is a red line over here. Since the plasma frequency is here, we can only use, approximately here, we can only use this band, which is around 16 measurement points to determine the temperature, and that is all. And an additional problem is that the plasma peak is not visible in the free solar wind. So we cannot determine the density just by hands. There is a lot of problems, so we had to work quite a lot to go around it. Okay. So, since the spectrum is linear, we can basically fit only one parameter. It only makes sense. And we do it for the temperature. So the density of the electrons must be approximated. We use data from quasi, which is a proton analyzer, which works, but still the results of quasi have quite a lot of question marks. And we assume that in average there is around 4% of the alpha particles. So electron density is 108% of the proton density. And we have that model which is very, very sensitive to these measurements. So the temperature can vary quite a lot for a single measurement and still stay within the measurement uncertainties. And in order to go around this problem, we actually need to average a lot of measurements over a certain period of time. So what we did, okay, it's not shown here, but what we did is actually to take the data not from one measurement, but from 1 hour of measurements. And then during 1 hour, we give a pretty rough assumption that the temperature is approximately the same. There is a bit of an algorithm that looks if there are so many crazy jumps, but mostly this is true, at around 85% of the time. And then we decrease the uncertainties of these measurements. So actually these uncertainties decrease as we take more measurements, which is logical, but at some point it becomes senseless because these uncertainties vary as the square root of measurements. That's the first thing. And the second thing, the temperature that we assume that is constant is not constant at long time scales over 1 hour. And from here we can actually give the average value of the temperature for 1 hour of time. This is what we can provide with uncertainty around 30 to 40%. This was a result that we were not thrilled about, but since on the mission we have nothing at this point, we found this as a decent progress. And then we need to verify the results. How to verify it? Well, we cannot compare it, as I said. Sorry, we cannot compare it with the electron analyzers on this mission because they don't work. But what we can do, we can compare it with the wind data. We make histograms for 10 months, and during these 10 months, the same values in the solar wind should appear the same number of times. And the first problem we found was that the density, this is the density from plastic, the blue histogram, and density from wind, they vary quite a lot. So there is much wider spread on this histogram than on this one. This one on red, which we trust in. This red one on wind, which we trust to. And consequently, we have the difference in the measured electron temperature. This is the wind temperature. This is the temperature on stereo, which we measured using our method. So, what we found out is that since we use this data, proton data, which still needs to be polished by the plastic team, and they are working on this quite hard as I speak. Since we have this data, then our temperature values are not going to be correct. But since the spectrum level is roughly proportional to the first moment of the velocity distribution, then we actually did the histograms of the first moment of the velocity distribution. And we found out that, in general, we have quite a good match between the numbers, between the values of the density times square root of temperature for 10 months of measurements. So this is a lot of measurements. And these spreads are actually coming. We did some statistical tests to confirm that. These spreads are coming due to large uncertainties on the stereo measurements. Okay, so what we need to do in order to give the database of the stereo electron density and temperature? Well, first we need more theoretical work, which is currently under progress. Now we can make a database. We have a method. It works. It gives results with uncertainty around 30 to 40%. It is fine, but there is a question of usability. What we need to do is to do some additional theoretical work and to develop the short noise theory at high frequencies. So this actually includes collective effects, a lot of plasma physics, and this is currently in progress. We've done the theoretical part, but there is also the numerics that needs to provide a readable result, and now we have pretty strong computers crashing down when we give them this task, but hopefully soon this will be done, and then we will be able to provide this and to cover around 85% of the flight time. So around 10, 11 years, 85% of that will be covered, and we will finally have the data which is missing since the beginning of the mission. Why just 85%? Well, because if there is dust on the radio antennas or some other non-thermal waves, then this signal is going to overwhelm everything, and we are not going to see the short noise. And we expect realistic errors around 30%, which is huge for the laboratory. For the space missions is acceptable, but still we are dependent on the plastic team that needs to give good, or at least better proton density measurements. They are giving each year, each version of the plastic data is better and better. First one was completely unuseful. But this is the current state, and we are working hard on this part, while the plastic team is working on this part. Hopefully soon, let's say at the end of the next year, but in science you can't promise anything, we will be able to give the good stereo database of the electron moments. Thank you.
Question? Yep. Thanks for good presentation and everything. You mentioned at the beginning, maybe you mentioned also my question, the answer to my question, but you didn't here. The particle, the electron detector gets become charged when it's surrounded with the low temperature.
Yep.
Is there some physical explanation why that happens and how they didn't predict it?
Yeah, it is the reason for that is actually inside the material, the solid material, and the word is, I can't remember in English, phase reality. What is the phase transition? Phase transition. Thank you. Phase transition. You have usually 4 to 5 phase transition after it becomes solid. So there are some critical phase transition inside these libraries that they used. And this is the precise physics. That's more question for people who develop the instrument.
They couldn't predict that before
well,
the mission.
they did test it up to some values, but this was just a miss on the instrument. Now at this point, everything for all future missions like MMS, like it was for solar orbiter, for solar probe, all these analyzers are now tested up to 77 Kelvin. So everything is frozen, and they're not letting this thing to happen again.
Thanks.
Okay, any question? Dejan?
Which are the energies for which you have kappa distributions? interval of energies for which you use kappa distribution?
You mean what is the thermal energy of the?
No thermal. I think it is non-thermal.
Yeah, it is. Okay, so basically.
Super thermal.
Yeah, of course.
Yeah.
So okay.
Kappa or this Lorentzian.
Here are the velocity given. Here's the velocity given. This part over here is usually the thermal part in solar wind is around from 25 to 10 eV as you go from the sun to the earth, and the suprathermal part, if you just define the kappa distribution for the suprathermals or another Maxwellian for the suprathermals, then the thermal velocity of this part, the thermal energy of this part is going to be around 5 to 12 times compared to the thermal part. So it's around, let's say, 10 times more than the thermal part on average. And then finally on these high temperatures, like 1 million or 2 million Kelvin, just if we look at the suprathermal part and we define this.
But in EVs?
Sorry?
But in EVs, in electron volts.
Yeah, in EVs it's like 20, it's 20 times 10, so 200, 150 to 200, 250. It's in the order of magnitude.
These are very, very low energies. Okay, thanks.
Yeah, something that we can detect with any kind of solid state detector. This is why you use them.
Okay, thanks.
Any questions? Okay, thank you very much.